Now we can talk about square roots. In many contexts in math, we know the square of a number and we have to solve for the original number that was squared. For example, we have something like x squared equals 5 and we need to find the x. If the square of the desired number happens to be a perfect square, then it's easy to solve. Getting x squared equal to a perfect square is a luxury that usually does not happen. Square roots and square root notation give us a way to talk about a situation in which the square of a variable does not equal a perfect square. Again, this is much more common than equaling a perfect square. For example, consider x squared equals 2. What number squared would equal 2? This would be a decimal between 1 and 2. We denote the positive number that, when squared, would equal 2 as, we use this notation. We read this either as the square root of 2 or radical 2. The square root and the act of squaring undo each other, precisely as addition and subtraction undo each other. This number, square root of 2 or radical 2, is a number on the number line, a decimal between 1 and 2. So it has a home on the number line. It does live there. It's between 1 and 2. In this way, the way that this number, radical 2, or the square root of 2, is connected to the rest of mathematics is by virtue of the fact that we know if we were to square it, we would get 2 as a result. That is the definition of the number. By definition, it is the number which, when squared, gives 2. We mentioned that the equation x squared equals 2 would actually have two solutions, one positive and one negative. When the radical sign is written, it means the positive root only. The other negative square root of 2 we would have to write this way. We'd have to put a negative sign in front of the radical, negative radical 2, or negative square root of 2. That would be the second root, the second answer to the left of 0. Many students get confused about this issue of whether to include or not the negative square root. When do you include the negative square root? When do you not include the negative square root? It turns out there's a very easy rule for determining this. If the radical sign is written by the test maker, written as part and parcel of the way the question is asked, so that sign is printed as part of the question, then that means consider positive roots only. That's always what that sign means. But if the problem contains a variable squared, or your calculations lead to a variable squared, and you yourself have to initiate the act of taking a square root yourself, so in other words, the square root sign is not printed as part of the problem, you're going to have to take a square root yourself in the act of solving the problem, then you always have to consider both the positive and negative roots. That's the difference right there. Whether the radical sign is printed on the test or not, that makes all the difference. So consider these two practice questions. These look similar, but they have different answers. Pause the video, work on both of these, and then we'll talk about these. Okay. Number 1, is the square root of 2 greater than 1? By square root of 2, by printing that sign, printing the radical sign, we by definition mean the positive root only. That positive root is a decimal between 1 and 2. So yes, it is definitely bigger than 1. That's perfectly clear. Now number 2 looks similar. K squared equals 2. Is k greater than 1? Well, now notice there's no radical sign printed. And so if I want to get the value of k myself, I have to initiate the act of taking a square root myself. That means I have to consider both the positive and negative because I'm doing it myself. So k would be either the positive square root of 2 or the negative square root of 2. And because it could be one or the other, we don't know whether it's larger than 1 or smaller than 1. So this answer cannot be determined. If q is positive, then square root of q is also positive. Can we take the square root of 0? Absolutely. We know that 0 squared is 0. So if we square it and get 0, we can certainly undo the squaring. That means that the square root of 0 equals 0. we can take the square root of 0 and it equals 0. So that's 100% legal right there. Can we take the square root of a negative? No. Positive squared are positive, negative squared are positive, 0 squared is 0. Nothing on the number line can be squared to yield a negative number. Now, as it turns out, there are higher forms of mathematics where they talk about square roots of a negative. It's called the imaginary numbers. You do not need to worry about this for the test. That is absolutely beyond anything that is on the test. So for our purposes, for the purposes of the test, for a is greater than or equal to 0, the square root of a is also greater than or equal to 0. If the test writes the equation square root of a equals b, radical a equals b, then by virtue of writing that with an equal sign, the test is guaranteeing that this is a sensible and completely valid mathematical equation. In other words, the test can never write an equation if the equation they're writing is not something that is mathematically legal. So this equation immediately tells us that a must be either positive or equal to 0, and b also must be positive or equal to 0. So both of those things are guaranteed right away. Technically, the radical sign is called the principal square root sign, which means that of the two possible square roots, this particular sign only returns the positive root. If the test says solve the equation x squared equals 5, then of course there are two solutions. The positive solution is x equals positive square root of 5, or principal square root of 5, radical 5. The negative solution is x equals negative radical 5. So those are two numbers on the number line. One is to the left of 0, one is to the right of 0, and they both have the property that when we square them, we get 5. The test will expect you to recognize and simplify square roots of perfect squares. So of course, radical 36 has to equal 6. The test absolutely will not expect you to come up with the exact value of a square root that doesn't come out evenly. So the test will not say, calculate the exact value of the square root of 41. That's out of bounds. The test will not ask that. But the test will expect you to know some basic approximations. First of all, for all positive numbers, the square root preserves the order of inequality. What do I mean by that? Well, if a is less than b is less than c, if they're in that particular order, the inequalities, then when we take the square root, they're still in exactly that same order. Square root of a is less than square root of b is less than square root of c. So that is true 100% of the time. If you have an inequality, you can take a square root of each term and it still preserves the order of the inequality. So we know that 41 is greater than 36 and less than 49. It's between those two numbers. So we can just simply take a square root of all three of those. And of course, the square root of 36 and the square root of 49 we can simplify. So this tells us that the square root of 41, whatever it is, it has to be a decimal between 6 and 7. So again, the test is not going to expect you to know the exact value. It is going to expect you to be able to figure out that the square root of 41 is a decimal between 6 and 7. Also, there are a few simple square roots for which you should know the rough approximations. Knowing these are very useful for approximations. If you just know these three to the nearest tenth, you can do a great deal of approximating, as we will see. The radical sign is an operator, just like addition, subtraction, multiplication, and division signs. All those are operators. And like those, it can operate on numbers or variables. We have to be mindful with this operator. It undoes squaring, but it is not an exact opposite. For example, suppose y is negative. Then y squared would be positive. Then the square root of y squared would also be positive. In other words, we don't wind up with the original negative number. We don't wind up where we started. So we have to be very careful. Because it's always positive, regardless of whether y is positive or negative, we have to say that the square root of y squared equals the absolute value of y. So in other words, if y is positive, then we get a positive output. If y is 0, we get 0. And if y is negative, we get a positive output. If a variable squared appears in a problem and we want to take the square root to undo the square, we always have to include the plus and minus sign. So again, the radical sign is not printed. We're the ones taking the square root. We always have to include that plus or minus sign. And in many cases, we'd have to just put that plus or minus sign right in front of a radical. So here's a practice problem. Pause the video and see if you can solve this. Now, of course, one way to solve this would be to FOIL that out. We have the square of a binomial, so figure out the square of that binomial, then subtract 16 from both sides, we get a quadratic. You'd factor that quadratic. That would be a long way to solve it. We have something squared. So notice all we have to do is take the square root of both sides. We're going to take the square root of both sides because we are initiating the act of taking the square root ourselves. We're going to have to include the plus or minus sign. So, taking the square root, we get x minus 3 without the squared equals plus or minus 4. Now we have two equations to solve. We have x equals 3 plus 4 and x equals 3 minus 4. And so x equals 7 or x equals negative 1. And those are the solutions. We also have to consider how square roots relate to the topic of exponential growth, which we discussed in the second lesson of this module. There we said if b is greater than 1, then positive powers of b get bigger. In particular, if b is greater than 1, then b is less than b squared. B squared would be a larger number. If squaring makes these numbers larger, then taking a square root must make these numbers smaller. And so the square root of b, or radical b, would have to be less than b. And that's if the base is greater than 1. But as we saw in that lesson, everything is opposite for positive numbers less than 1. If the base is a number between 0 and 1, then positive powers of b get smaller. In particular, if b is between 0 and 1, then b is greater than b squared. B squared would actually be a smaller number. If squaring makes these numbers smaller, then taking a square root must make these numbers bigger. So for a b that is between 0 and 1, it must be true that the square root of b is greater than b. Think about the number 2/3. This is a fraction greater than 1/2. If I square it, that is multiply it by itself, what I get is 4/9, and that's a number less than 1/2. Therefore, it must be true that the square root of 4/9 is 2/3. And of course, 2/3 is greater than 4/9. So the square root of 4/9 is greater than 4/9. And that's always true for a number less than 1, a positive number less than 1. The square root is always greater than the number itself. Here's a practice problem. Pause the video and then we'll talk about this. If 7k is a positive integer and if square root of k is greater than k, then is k an integer? Well, the square root of k is greater than k. That only happens when k is less than 1. So k must be a number between 0 and 1. It can't possibly be an integer. It would have to be either 1/7 or some multiple, 2/7, 3/7, something like that. And so we definitely know that it's not an integer, and the answer is B, a clear answer of no. In summary, the radical sign always has a positive output. If we take the square root ourselves, we must consider both positive and negative roots. We covered some basic approximations for square roots. If the base is greater than 1, then taking a square root makes things smaller. Square root of b is less than b. If the base is between 0 and 1, taking the square root makes things bigger. Radical b is greater than b. In this lesson, we're going to talk about other roots, cube roots, fourth roots, this sort of thing. So, just as the square root more or less, quote, undoes the act of squaring, of course we learned that that's not exactly true, there are higher order roots that similarly undo the other powers. For example, cube roots undo the act of cubing something. So just as we can raise something to the third power, we can find what number raised to the third power would equal a certain result. So first of all, let's talk about the notation. Square root of k, radical k, denotes the square root of k. The notation for all other roots is similar. We use the same radical symbol, but for all other roots, we put a small number in front of the radical to denote the order of the root. In other words, are we taking a cube root, a fourth root, a fifth root, etc. So for a cube root, what we would do is put a little 3 in front of the radical sign, and that would denote the cube root of k. We also have to think about positive and negative, because positive and negative numbers get kind of tricky here. Remember that, first of all, with squaring, a positive squared is positive and a negative squared is also positive. Okay? So this is true for squaring. Therefore, it's true that if we have x squared equals a positive, that has two solutions, one positive and one negative. For example, x squared equals 9. It could be plus 3 or minus 3. By contrast, x squared equals a negative has no possible solution. X squared equals negative 9. There's no real number that satisfies that equation. The positive and negative roots for cubes are a little bit different. Remember that if we cube a positive, we get a positive, but if we cube a negative, we get a negative. Therefore, x cubed equals a positive has one positive solution, and x cubed equals a negative has one negative solution. So you don't get the problem of double roots in one case and no solution in another case, as we got for squaring. With square roots, we can find the square root only of positives. Of course, we could also find the square root of 0, but we cannot take the square root of a negative. Okay, so for much the same reason, just as we can't square something and get a negative, we can't take the square root of a negative. But the rules are very different for cube roots. We can take the cube root of any number on the number line, positive, 0, or negative. So every single number on the negative line, we can raise it to the third power, and we can find the cube root of it. So for example, the cube root of 8 is 2, the cube root of 0 is 0, and the cube root of negative 8 is negative 2. So unlike the square root, the cube root can have a negative output. When we put in a negative, we get out a negative. For quick computations, it's good to have the cubes up to 10 memorized. Certainly the first 6 are very important to memorize, and really if you know all 10, it's kind of a time saver. And a couple things I'll point out. Notice that 8 cubed, of course that would be 2 to the 9th. Notice that 4 cubed, that's 2 squared cubed, so that would be 2 to the 6th. It would also be 2 to the 3rd squared, or 8 squared. And of course 8 squared is 64 also. So there are some patterns here that we can observe practicing our laws of exponents. So if we have these cubes memorized, automatically we have a bunch of cube roots memorized. And so that can be very convenient. Cube roots are relatively infrequent on the test, and higher order roots, fourth root, fifth root, sixth root, are even more rare. So these are not very likely topics, I'll warn you right now. But I'll say a few things in general about all roots. So this is true for every possible root, square root, cube root, etc., etc. We're going to talk about all the patterns here. First of all, the square root of a, the fourth root of a, the sixth root of a, etc., these are called even roots. So when we have an even number written there, it's an even root. And of course with a square root there's an implied 2, so that's an even root also. The cube root, the fifth root, the seventh root, these are called odd roots. So we're distinguishing all the even roots from all the odd roots. And the reason we're doing this is because the same positive and negative thing we've talked about with squares and cubes extends to all the evens and odds. As with square roots, we can take any even root of a positive number, which results in a positive output, but we cannot take an even root of a negative number. We try to take an even root of a negative number, it is undefined. It does not equal anything on the number line. By contrast, as with cube roots, any odd root of a positive is positive and any odd root of a negative is negative. So it follows that same plus and minus pattern. For other properties, I will use the notation with an n before the radical sign. So the nth root of a. And here I'm talking about a general root, and of course it's understood that n is an integer greater than or equal to 2. For all roots, we can take the nth root of 0 and it equals 0, and the nth root of 1 equals 1. So that is true for all values of n. All roots preserve the order of inequalities. So if we have 3 numbers in a row, as long as they're positive numbers, we take the roots of them, as long as it's the same root we're taking of each number, then they remain in that same order of inequality. For example, suppose we had to estimate the 4th root of 50. Well, we'd want to locate it between two 4th powers. Well, 2 to the 4th, we know, is 16. 3 to the 4th is 81. So, because 50 is between 16 and 81, we can take the 4th root of all of those, and we see that the 4th root of 50 would have to be a decimal somewhere between 2 and 3. So the test is not going to expect you to do anything more fancy with finding the 4th root of 50, but as long as you can figure out which two integers it's between, that is fine. We can also compare the size of different order roots. So for a number greater than 1, the higher the root, the smaller the actual number. So the nth root is a higher order root than the mth root, and the nth root is smaller. So let's think about this. Suppose we're taking different roots of 19. Well, of course, the square root of 19 has to be smaller than 19. Now, the cube root of 19 has to be even smaller because it only takes 2 of the square root. If we multiply 2 of the square roots together, we get 19. We'd have to multiply 3 of the cube roots together to get 19. And then we extend this logic. Well, the 4th root has to be even smaller because I'd have to multiply 4 of them to get 19. I'd have to multiply 5 of these or 6 of these and so forth. So it means that as we get higher and higher order roots, all of these numbers get smaller, but they're always larger than 1. Now, it must be true, even if we can't figure out what the decimals are, it absolutely must be true that the 30th root of 19 is less than the 20th root of 19. So in other words, we should be able to make that comparison even though we can't figure out the exact values of those decimals. Now, when we get into that region between 1, 0, and 1, then things get a little bit different. And you may remember things were different here. First of all, we take a root, the roots are bigger than b, assuming that b is this fraction between 0 and 1. And the higher the order of the root, the higher it gets. So n is a higher order root. It's higher. The nth root of b is higher than the mth root of b. So suppose we're taking different roots, say, of 2/5. Well, 2/5 is less than the square root of 2/5. This is going to be less than the cube root, which is less than the 4th root, and so forth. We continue this pattern. It turns out that all these roots remain less than 1. So they get bigger and bigger and bigger, but they never get as big as 1. And this pattern continues with all higher order of roots, so even if we had to compare two very high roots, we could say, for example, we'd know that the 50th root of 2/5 that has to be greater than 2/5, but it has to be less than the 75th root of 2/5, and the 75th root of 2/5 still has to be less than 1. So we should be able to figure out where these four terms fall in an inequality, even though we can't figure out the exact decimal values of those roots. One way to summarize is we could say the higher the order of the root, the closer the result is to 1. That is, with numbers bigger than 1, taking higher order roots make it smaller and smaller, move it closer to 1. Taking roots of numbers between 0 and 1 makes it bigger, and they move up closer and closer to 1. So this is the pattern. Everything gets closer to 1. And one of the reasons for that, of course, is that we can take any root of 1 and it equals 1. These properties are rarely tested and only on the hardest quant problems on the test. So once again, this is not something you're going to see every time you sit down for the test. These are very rare problems. In summary, unlike with square roots, we can take cube roots of both positives and negatives. That's a big idea. In fact, we can take any even root of positives only, not negatives, but we can take any odd root of any number on the number line. That's also a really big idea. Any root of 1 equals 1, any root of 0 equals 0. All roots preserve the order of inequalities, assuming all the numbers are positive. And the higher the order of a root, the closer the result is to 1. So again, the number is larger than 1. When we take roots, they get smaller, move closer to 1. When we take roots of numbers that are between 0 and 1, they get bigger and they move closer to 1. Properties of roots. Fundamentally, roots are a special case of exponents. So some of the properties of exponents are the same as the property of roots. In a couple lessons from this one, we will make clear the link between roots and exponents. That's something we'll discuss in a little more depth. Right now, we'll just focus on a couple big properties of roots. In all the following examples, I'm going to use square roots and assume that the numbers p and q are positive. In fact, all these properties work for all higher order roots as well, and for the odd roots, the numbers don't even have to be positive. So I didn't want to clutter up the notation with nth roots everywhere, but just so you know, everything I'm talking about with square roots here, this actually extends to higher order roots. It's just rare that you would have to use that on the test. Remember that exponents distribute over multiplication and division. Roots also distribute over multiplication and division. So the root of a product is the product of the roots, and the root of a quotient is the quotient of the roots. The multiplication property makes some simplifications much easier. Suppose we're told that we had to simplify square root of 12 times square root of 27. Well, one way to go about this is we could multiply them together, and of course we're not just going to multiply out and get that horrible 3-digit number. Again, we're going to think about this. We're going to factor out a 3 from that 27 because that will leave us with the perfect square 9. And that factor of 3 I'll multiply by the 12. Well, when I do that, I get another perfect square. So I now have the square root of 2 perfect squares. Separate them out, take the square root of each, and it's 6 times 3, which is 18. So it must be that whatever 12 times 27 is, that must be 18 squared. But fortunately, we didn't have to figure out that number in order to perform this simplification. And we'll explore this much more in the next lesson. The division property makes it easier to simplify the square roots of some fractions. So for example, if we had the square root of 4 over 49, we can just take the square root of each one of those numbers individually, and that equals 2/7. If we had the square root of 4 over 50, of course we can simplify a bit first. We can cancel a factor of 2, then take the square root in the numerator and the denominator. In the numerator, we can't do anything else. Square root of 2, we're stuck with that. But in the denominator, we can simplify that to 5. So these are two fractions that get a little bit simplified. And we're going to discuss this process in much more detail a couple lessons from now. This will be a problem of what happens when you get a square root in the denominator. That didn't happen here, but it is a problem, and we'll talk about it in a few lessons. As with exponents, there is also a very tempting mistake to make here. Roots do distribute over multiplication and division. Roots do not distribute over addition and subtraction. So it's very tempting to say that square root of p plus square root of q, to set that equal to the square root of p plus q, or the same with subtraction. It's a very tempting mistake to make, but it is simply not true. We will see a very important application of the multiplication rule in the next lesson. In summary, roots distribute over multiplication and division. Roots do not distribute over addition and subtraction. Now we can talk about simplifying roots. And this is a very important topic on the test. You see, because often we have to take a square root in a problem, and the problem itself will result in the square root of a large number, but the square root of a large number will not appear among the answers. The answer choices will be in simplified form, so we have to recognize how to simplify a radical. So if we have something large like square root of 75, how do we simplify that and write it in a form that would appear in the answers? So that's what we're going to talk about here. As we learned in the previous lessons, roots distribute over multiplication, so we can separate a root of products into a product of roots. So if I have a product under the roots, I can separate that into the square root of the first one times the square root of the second one. First of all, remember, it is easy to find the square root of perfect squares. As a reminder, here are the square roots of the first 15 perfect squares. So square root of 49, we're asking what number do we multiply by itself to get 49, and of course the answer to that is 7. And similarly for all of these. And these are just good numbers to know. Now, as we learned in the previous lessons, roots distribute over multiplication. So as we said a moment ago, we can separate the root of a product into the product of the roots. So the root of the product, p times q, equals the product of root p times root q. And now notice, if p or q is a perfect square, then that square root would be very easy to simplify, and the entire expression would simplify. So for example, suppose at some point in a problem we needed the square root of 75. Maybe the answer to the question is the square root of 75. Well, square root of 75 is not going to appear in the answer choices, but clearly 75 is a multiple of 25, and 25 is a perfect square, so we can use that to our advantage. So I'm just going to write square root of 75. It's not going to appear in that form, but I'm going to write that as a product of 25 times 3. Now I can separate the roots, and now square root of 25, that's something I can simplify. Square root of 25 is just 5, and I can just write this whole thing as 5 root 3. So 5 root 3 is equal to the square root of 75. It is the simplified form of the square root of 75. So the form square root of 75 would never appear as a multiple choice answer on the test. It would always appear simplified as 5 root 3. And that's why it's important to know how to do this procedure of simplifying roots, because we have to make the answers into a form recognizable on the test. The way the test itself will list the answers. So here's some more to practice. Pause the video and then we'll talk about this. Okay, in each case what we're doing is we want to express the number under the radical as the product of a perfect square times something else. So 12 is divisible by a perfect square. It's divisible by 4. So I'm going to write it as 4 times 3. And then, of course, square root of 4 is just 2. So then this is just simplifies to 2 root 3. 63, I can write that as 9 times 7. And square root of 9 is 3. So this becomes 3 root 7. 80, I can say that it's divisible by 4, but actually it's also divisible by,
we divide it by 4, we get 20, we can divide by 4 again. In other words, 80 is actually divisible by 16. And so we actually save a bit of time if we write this as 16 times 5. And the square root of 16 is 4, so this is just 4 root 5. And then 175, well, that is 7 times 25. So 25 times 7, take a square root of that, and what we get is 5 root 7. And those are all simplified roots. And so in the test, you'd never see square root of 175 listed as an answer choice. You'd see it listed as 5 root 7, the simplified form. Suppose the number beneath the radical is particularly large. Suppose we have to find the square root of 2,800, for example. It certainly will help to factor out larger squares, such as 100. It may be necessary to find the full prime factorization of the number. Here we can simplify immensely simply by factoring 100 out of the radical. So square root of 100, of course, is 10, so this just becomes 10 root 28. But 28 I can also simplify. That's 4 times 7, and the square root of 4 is 2. So it's 10 times 2 root 7, or in other words, 20 root 7. And that is, in fact, the fully simplified form of the square root of 2,800. Here's a practice problem. Pause the video, and then we'll talk about this. Okay, well, first of all, we know we cannot add through the radicals, so we certainly can't add 48 plus 75 plus 192. So instead, we have to simplify each one of those radicals. So let's take them one at a time. 48 is certainly divisible by 4. It's 4 times 12, but 12 is divisible by 4 again. So this means that 48 is actually divisible by 16. So we can write it as 16 times 3. Of course, the square root of 16 is 4. So the 16 comes out of the radical as a 4, and we just get 4 root 3. 75 we've already looked at. This is 25 times 3. 25 comes out of the radical as 5. So this is just 5 root 3. Right away, very interesting. The first two are both multiples of root 3. Makes us think what maybe the third one would be a multiple of root 3. What happens if we divide 192 by 3? Well, we know that 180 is 60 times 2. 60 times 3. And so subtract 192 minus 180, that's just 12. And of course, that 3 goes into 12 4 times. So 3 goes into 192 64 times. So this is actually 64 times 3. And that we can really simplify because 64 comes out of the radical as 8. Square root of 64 is 8, so we get 8 root 3. Well, now we've simplified all three. So all three are in simplified form, so we can simply add them. So 4 of anything plus 5 of that same thing plus 8 of that same thing has to be 17 of that thing. So the whole thing just simplifies to 17 root 3, and we choose answer choice A. In summary, we simplify square roots by factoring out the largest perfect square factor. If we can find the prime factorization, or if it is given, then we can use that. Any pairs of prime factors and any even powers of primes are perfect squares. So that can be helpful too.
Operations with roots. The test will expect us to do all kinds of arithmetic with roots and radical expressions. For example, it might ask us to add or subtract radicals. It might ask us to multiply them or raise them to powers. Each one of these we will address at some point during this lesson. I'm just listing these as examples to give you an idea. This whole lesson is about doing arithmetic with radical expressions. So first of all, we'll start with addition and subtraction. And in fact, we'll begin with what we cannot do. As we discussed in the previous video, we cannot add or subtract directly through the radical signs. So for example, if we had to do root 72 minus root 32, it would be incorrect to do the subtraction and get square root of 40. It's an extremely tempting mistake, but it is 100% wrong and mathematically illegal. And it's very important to appreciate this, because when your mind is under pressure in the test, your mind is going to be drawn to making a mistake like this. So it's especially important to be clear about this so that you don't make this mistake when you're under pressure. Instead, when we have a sum or difference of radicals, we have to simplify each radical separately by itself. And then we can add or subtract the ones that have the same radical factor. So for example, if we have to subtract root 72 minus root 32, the thing to do is treat each one alone by itself and simplify it. And in fact, this is another application of simplifying square roots, which we learned in the previous video. It turns out that we use this skill often in problem solving. So we'll simplify square root of 72. Of course, that's 2 times 36. Separately, we'll simplify the square root of 32. That is 2 times 16. And of course, we can simplify both of those down to 6 root 2 minus 4 root 2. Well, now we have the same radical factor. And in fact, 6 of anything minus 4 of that same thing would have to equal 2 of that thing. So it has to equal 2 root 2. Notice that we can combine two terms only if they have the same radical factor. The expression 6 root 2 minus 4 root 3 cannot be simplified any further because those radical expressions are not equal. Now we'll talk about multiplying and dividing radical expressions. Remember, first of all, that multiplication is commutative and associative. What does this mean? It means when we're multiplying things, we can swap the order around in any way we like. As long as everything is multiplied together, we can choose which pieces get multiplied together first. We can do them in any order. We have a lot of choice about the ordering and the arrangement of the factors. So suppose we have to multiply two radical expressions. Now think about this. There's a lot of multiplication here. 3 times the square root of 5 times 7 times the square root of 2. So really what we have here are 4 separate factors multiplied together. Well, of course, these 4 factors can be grouped in any way. So we're simply going to group the whole numbers together, multiply whole numbers by whole numbers, and group the radicals together, multiply radicals by radicals. So we'll group the 3 and the 7 together, and separately we'll group the root 5 and the root 2 together. And of course, we multiply right through the radicals, so 3 times 7 is 21. Root 5 times root 2 is root 10. We get 21 root 10. Sometimes we get a product under the radical that we can simplify. So when we multiply these, of course, the 3 times 2 will give us a 6 outside the radical. Under the radical, we're going to have 5 times 15. And rather than multiply that, I'm going to break the 15 into factors. Because when I do that, it becomes very clear I have a 5 times 5. 5 times 5, I can take a square root of that. In fact, the square root of that, the square root of 5 times 5 would just be 5. So I get 6 times 5 times square root of 3, which is 30 root 3. Those are relatively small numbers. Things get trickier when the numbers are bigger because the product of radicals can almost always be simplified. So for example, suppose we had something like 2 square root of 42 times 4 square root of 63. Well, of course, the 2 times 4 is 8. That's easy. Underneath the radical, I'm going to have 42 times 63. Well, pause right here. At this point, the absolute worst possible thing you could do would be to find the product of 42 times 63. So, of course, if we multiplied 42 times 63, we'd get a number larger than 1,000. Whenever it comes to a point that you have a choice, you can multiply two numbers and it will wind up with a number larger than 1,000, rest assured that performing that multiplication gratuitously is the absolute wrong thing to do. It's much easier to leave things in product form, and in fact, it's going to be easier to break it down even further to express this in terms of factors. So you don't want to get bigger, you want to break it into small pieces because those are easier to manage. So instead of performing that multiplication, we're just going to find the prime factorization of both of those. Well, this makes it very clear that we can pair up some factors. So I'll just group them like this. The 3 times 3, I can take a square root of that. The 7 times 7, I can take a square root of that. And then, of course, we have the extra 2 and the extra 3. We can't simplify those. Those will have to stay under the radical. But I do get 8 times 3 times 7 times root 6. 3 times 7 is 21. We don't need a calculator for this. 8 times 20 is 160. So 8 times 21 has to be 168. So it's 168 root 6. Notice in all of that, we multiplied whole numbers by whole numbers, and separately, we multiplied radicals by radicals, multiplying through the radical signs. One big mistake is to multiply a whole number through a radical sign to the number on the inside of the radical. So, for example, if we had 2 root 6, to multiply that to get root 12. Again, this is the type of mistake it's very easy to make if you're under pressure. So it's very important to pay attention to this. The big idea here is keep separate what's under the radical and what's out in the open. As long as you keep those two separate, you'll be fine. Similarly, if we divide whole numbers by whole numbers, and we divide radicals by radicals right through the radical signs. So if we had something like this, we separate it out into whole numbers and radicals. As it turns out, 54 is a multiple of 18. 18 times 3 is 54, so that will simplify to 3. We can divide 35 divided by 5 right through the radical, and we get 3 root 7. Now, as it turns out here, we had an extraordinary coincidence. We have an example in which the radical and the denominator canceled completely. Now, as it turns out, in general, the radical and the denominator will not cancel, and we're going to have to do something with that radical and the denominator. So that's a large topic. We're not going to discuss that in this video. That is a video all to itself, the video on rationalizing, which is a couple lessons from now. So the larger topic of how to divide by radicals, we're just going to put this off and discuss it in great detail in a couple videos from now. Finally, we'll talk about raising radical expressions to powers. Remember that exponents distribute over multiplication. Thus, if we're squaring a radical expression, we can square the number and the radical separately. So if we have 5 root 6 squared, we can just take that exponent of 2 and distribute it to each one of the factors separately. Well, of course, we know how to square 5, and we know how to square the square root of 6. The square root of 6 is the number which, by definition, if you square it, you get 6. So, of course, we square the 5, we get 25. We square the root 6, we get 6. Multiply those, we get 150. On harder quant questions, the test might ask you to raise a radical expression to a higher power. This is less likely, but it could appear in a problem. For example, suppose we had 2 root 3 to the power of 4. I'm going to suggest pause the video here and see if you can figure out what this equals. Okay, so one way to approach this is just to apply that exponent of 4 to the two items separately. Apply to the 4, apply to the root 3. Well, 2 to the 4th, that's 16. Root 3 to the 4th, what's that? Well, anything to the 4th just means that thing times itself 4 times. So we'll just write it that way. And of course, root 3 times root 3 is 3. So really what I'll get in that parenthesis is 3 times 3, which is 9. And then 16 times 9 is 144. So that's one way to get to the numerical answer. Another way to attack that same problem is to notice that we could write that 4 as 2 times 2, and then bring only one of the factors of 2, bring that exponent inside the parenthesis. So we'll have a squared inside and a squared outside. Well, the squared inside, that's easy. We just talked about how to square things like this. So 2 squared is 4, root 3 squared is 3. That's 4 times 3, or 12. Now we can apply the outside squaring, and that gives us 144. That's another way to approach the same problem. In fact, that way might be a little more elegant. It's always good to appreciate cases in which there's more than one way to solve a problem. Keep in mind that any even power of a square root can be written as a power of a whole number. So for example, if we had to deal with square root of 2 to the power of 48, well, all we have to do is really realize we can write that 48 as 2 times 24, and then bring that 2 inside the parentheses. So this is root 2 squared to the power of 24, which means that is 2 to the 24th. We can't compute the numerical size of that, but we still could compare the size of that to something else. For example, we can see that the square root of 2 to the 48th has to be bigger than 2 to the 20th, because that first term equals 2 to the 24th. In summary, when we add or subtract radical expressions, we simplify each term and combine terms with like expressions. When we multiply or divide radical expressions, we can treat the whole numbers and radicals separately, and we can multiply or divide two radicals right through the radical. When we raise a radical expression to a power, we distribute the exponent to each factor, and any even power of a radical is a power of a whole number.